Today we're going to have a look at a real data set and how do we start to understand what is in it. So one of the things that is always a little misleading is when you look at the documentation, you find all of these different fields and different values that are documented and can happen in the database. But when you look in the database, you often find that most of these rarely happen. So even though the database says that there would be some information there, the information is almost non-existent. So it is important when you do statistical analysis that you find that part of the data that is dense, that you have a lot of data with common properties so that you can do some statistical analysis. Because if you don't have a large enough number of records for a particular quantity that you want to calculate, like an expectation or a variance, then you would get values that are very unreliable and can't be used. So the better way to do it when you can is to eliminate the things that are like only little pieces of information that confuse you more than they can help you. Okay, so we're going to start on this weather data set by counting the number of records for each measurement. So there are different types of measurements, and what we have here is an SQL query that will look for each measurement, count the number of records that have this measurement, and return that as a data frame, as a Spark data frame. And then using this command here, it would translate this Spark data frame into a Pandas data frame, which is easier to work with and is going to be in the head node. Okay, so there are 133 different types of measurement in the data. And we are going to look at what are the most common ones. So here they are. We see that for precipitation, we have about 2.5 million records. And then for T-min, we have about 1 million, 1 million, and so on. And things drop off pretty quickly. What we're going to look at is just the 30 most common measurements out of those measurements that we had there. And the way that we do that is by constructing this quite elaborate SQL query. This SQL query was not typed into the computer. I generated using a little loop that generates this string that would be used as part of the query. You can see the details in the notebook. So when we look at that, we now have 30 of the most common one, and we can see that the 31st one has less than 15,000 records, while the top one had about 1.5 million, 2.5 million. So what next we're going to do is we're going to look at those more common measurements, and we're going to count for those measurements. We're going to look at each year and say, well, how many days of the 365 days have actual values in them and how many are undefined. And what we will find might surprise you. So how are we going to do that? We want to basically do a kind of map operation on a data frame. Data frames don't allow map operations, but they allow something similar called user-defined functions. So user-defined functions, basically here a Python function. What this function does is unpacks the values and then it counts how many of them are undefined. That's what it returns. And what we're going to do is we're going to register this function as a UDF. Okay, so Data frames allow you to give your own functions, but you have to register them so that they know all of their properties so that they can optimize for these functions. And then this is how you use the UDF to add a new column called nan number, so number of nans. And this function is basically the application of the UDF function to the values field in weather data frame. Okay, so this is the format that you use. And what you see here is that data frames are in a way more flexible than RDDs because you can add new columns to them. Okay, so you can basically create a new column without recreating the whole data frame. So now that we have this data frame, we want to compute the histograms. We basically want to know what is the distribution of the number of missing values. So we're going to use map and reduce here to calculate the histogram, or the number of times that you have 5 undefined or 6 undefined and so on. And so how are we going to do that? We basically first map each count, so each record has a count of the number of undefineds, to the vector of 365 zeros with a single one at the location of the count. Okay? And then we create a histogram by adding these vectors. And this addition of vectors is done by a reduce by key. Okay, so here is our little function that, given a number n, generates a vector of length 366, such that all of the locations are 0 other than location n that is 1, and it returns it. And here we're just doing this mapping. Okay, so we're generating for the non-RDD, we're generating this table that has measurement, and then for each one of the measurements, the type of the measurement, and then the vector that has a 1 in a single place. Okay, and then we compute the histograms by using reduce by key, so reducing for each measurement separately. We're just basically summing. So this summation is done really using NumPy, because these are NumPy vectors, and that's what generates the final histograms. So finally, we can now plot the histograms, and this is what we see. So let's have a look at it. So first of all, the first 1, 2, 3, 4, 5, 6 measurements that also have the highest numbers of count. Remember, precipitation has 2.5 million. They also, most of the time, have 0 undefined, or 0 or 1 undefined. But after we go from this step, we look at the next ones. Almost all of them have almost nothing defined. Okay, so most of them have 365 undefined, and we go on like that. And then there are some special cases like this one that has some measurements but distributed throughout. This one that actually has quite a lot of measurements but is still a pretty small data set. And then these that have other kind of phenomena. One of the interesting things just to look at here, and also here and here, is that you have, if you count them, exactly 12 spikes between 0 and 365. So 12, what do we have? 12 months. So that's an interesting thing. It turns out that these data sometimes are collected once a month. Somebody goes and collects the data. So when you have a missing month, you get a spike like that. So you have that it is a month you either have the whole month or you don't have the whole month. So that's where you get these kind of funny curves. So you can do various forensic work to identify them. But basically what we see is that in this data set, these first 6 elements are strong and big and have a lot of defined values. So we're going to use those. And we're basically going to not use any of the rest because unless we have some particular reason that we want to look at some other data, this data is much more sparse than what we have here. Okay, so for most stations, for most years, we have precipitation. It's rarely that we have this evaporation data. So to summarize, before we analyze a large data set, it is important to know how dense it is. So we always want to go in and calculate some averages of the whole thing and so on. And we also want to count how many of the values, of the discrete values appear for each value, right? Because often the case that for some of the values you have a lot of measurements, and for most of the values you have almost no measurements. So that is something you want to kind of clean up before you go further. What we choose to do here is to restrict ourselves to these 6 first measurements. And I suggest that you consult this file to see this documentation file to see what these are. So that in the notebook there are directions about how to download that file. See you next time.